Today experiment is about the carbohydrate lab. Carbohydrates. So carbohydrates are sugars, correct? And this is mono sugars or called saccharides, correct? So saccharides. So they are mono, they are di, and they are poly saccharides, of course, correct? Disaccharides, monosaccharides, polysaccharides. Those are sugars. So just an example of what I can go through all this here. For one of the most important one, which is glucose. Glucose, 6 hydrogens, C6H12O6. So the glucose is a monosaccharide, which is very, very important for sugar blood. And the disaccharides like lactose. Lactose is made of, or maltose. Maltose is made of 2 sucrose, maltose. That's an example here. 2 glucose together. Or sometimes glucose, and not glucose here. Yeah, glucose plus glucose, lactose here. Hold on. The second one is lactose. Plus glucose. So we have maltose, 2 glucose, and then we have lactose plus 1 glucose. Lactose is like glucose, but the carbon is different. I'll show you in a minute. The poly is starch, which is multiple glucose. So you have over 300 glucose together, over 300, correct? So we have maltose, we have lactose. We can show you in a minute here. So here they are. Just show you that you have the 6 carbons connected through the galactosidic. This is how many carbons we have. You can calculate 1, 2. Each of those here is carbon. Each of those here is carbon here, carbon here, carbon here, and here's carbon. So 1, 2, 3, 4, 5, 6. That's a glucose, correct? That's a glucose. So we'll talk about the reaction in a minute, but that's a glucose. Let me show you the other ones. So here they are. Glucose. This is the glucose. This is the X and Y drawing of it, this line structure. But this is the 3D type of structure. So you can see in details up and down. That's a 3D. That's a real 3D. So the flat ring is like this and sticking out and sticking down. The H's and the CHOH. So this is glucose, and the glucose by far is the backbone of carbohydrate. When you speak about carbohydrate, you speak about glucose because it's really contributing to all types of glucose themselves. So this is a glucose
So what you will see here, that's the 1 and 5. 1 and 5, they're coming. 1 and 5, they're coming together and they close each other in a ring. Correct? So if you look at this, that's the glucose. And this is the hemiacetal group. As you can see here, the hemiacetal is one acetal. So the hemiacetal, you have C, OH, H, and OR, and H. So you can see here all OH here. So here it is, CHOH, correct? Then to C, now if I replace this one here with OR, then will be complete acetal. That's a hemiacetal with just, here you have H, correct? So you have what? You have H there. So this is a semi, not complete acetal, because you don't have two ORs. You have only one OR. This is one. That's the OR here. Oxygen and then the rest. So that's a semi-acetal or hemiacetal half of not complete acetal. This is a glucose in the line structure here. And here is a ring structure, correct? Which is the most stable form of glucose is the ring. The ring of most of the carbohydrates, the rings, the cyclic structure is the most stable one than just the straight line structure. So now the important thing is to know the OH at the number 1. Let me take this one out. I have to know exact situation of this and this. Okay? Down is alpha. Up, the OH is up. That's beta. Alpha OH down. So that's the first thing of this. Okay, guys? And if you look at number 4, this is your down. This is your up in the cyclic. That's a cyclic structure. Cyclic. So in the cyclic, the right line structure will be down. In the left one, the right one is down. The left one is at the top. So you can see the OH is here, correct? Is down. So it will be what? It will be alpha. And the one and connected to what? One is here to what? To number. This is coming from number 5. So 1 and 5 connected together. So now, if this is down, correct? If it's down here, this number 5 is down. This will be your D. If it's up, your L. So L and D. So this is D. Down or right in the right, or here left. So now we know what those are. D is the alpha first. The alpha is coming from this. This is alpha, and this is the D1, correct? And that's what the D1 we can differentiate between glucose and galactose. Galactose is, in the galactose, the OH is up. The glucose, the OH is down. So this is alpha D glucose. Okay, guys. Now let's look at the what's that? Yeah, I don't know. It's malfunctioning. The alarm is malfunctioning. So then we have a fructose. Fructose is different from the glucose. Glucose is we call it 6-member carbohydrate. This is 5-member. So you see the ring is 5. The ring is 5-member ring or the cyclic form. This is the most stable one than this. Fructose is a ketose. So what is really carbohydrate? Carbohydrate is nothing less than aldehydes and ketones, but special ketones and special aldehydes. Why they are special? Because they have multi-hydroxy group. So if they have multi-hydroxy group, the stability will come from hydrogen bond. It's not mentioned here, but at least you know they form a lot of hydrogen bond with H2O. So they are highly soluble in H2O due to the fact they are making with H2O hydrogen bond. It's not stated in your lab procedure, but at least a hydrogen bond is very, very obvious when it comes to the carbohydrates. So that's ketose, and the ketose will form ketones called ketones. Or from the ketose, we call them ketose. OSE means carbohydrate. From aldose. So take this will be aldose. So ketose and aldose. So from aldehyde, aldose, from ketones, ketose. So 5-member ring, and you can see that's the whole thing. So here we have 2 groups of CH2OHs. Here we have only one up there. And you watch for number 4 OH. The OH will give you down or up. And here, up or down. So always watch for this. They are very, very important for this. Okay, guys. So here it's why it's better. Somebody will tell me why it's better. That's D-fructose, but why it's better? Somebody will tell me why it's better. Because the OH is what? Is up. Here the OH is down, is what? Alpha. So you see the difference between them? So this is monosaccharide. This is monosaccharides. So that's monosaccharides means one single molecule. And they have a lot of OHs. They are highly soluble in H2O because they can make hydrogen bond. So let's now we have the disaccharide. Disaccharides are the sugar, the kitchen sugar called sucrose. Sucrose is made of combination of glucose and fructose. So you have, this is a glucose, and this is fructose. So combine them through this link, and then when you hydrolyze them, the enzyme or acid, as you will see today, you'll do it in the acid. So you can make out of this, the original one glucose and one
fructose. Okay, guys. So this is the disaccharides. So here, examples of disaccharides. You can see here different ones. And the unique thing you have to watch here anytime, even in the lecture. So you have to watch for this type of the connection. This is gallosidic bond. Once they have the direction between 1 and 4 carbons, between 1 and 4 carbons. And alpha means down. The OH was down, alpha. This is alpha. And the connection between carbon 1 and 4. This is carbon 1. This is carbon 4. Okay, guys? So that's maltose. Maltose, two sugars, two glucose together, correct? Now you can have the alpha glucose and you can have beta glucose if the OH, one OH is the top, that's like the OH was in the top, so it will be beta. Okay, 1,4 beta. Now this one here is sucrose. Sucrose is made of glucose and fructose, and the link between 1 and 2, So it's 1 is down, and the 2 is going up. So you have connection alpha D. This is 1,2 bond, and this is alpha beta D fructose. So this is up, and this is down. So you have those type of connection. So just to get you familiar with this, nobody will ask you in the exam, but at least you will know how to make differences between this. And the last one is starch, cellulose, glycogen. So glycogen, cellulose, and starch. So the starch, when it's a multiple, correct? It's a multiple amount of what? Of glucose. So the starch, I think, over multiple. So, and if you go for the cellulose over maybe 200, 300, or 400 of glucose combined together. So, for example, all of those are glucose. So they are lining up in the line. So those glucose and connected with oxygen in the middle. So that's the way those polysaccharides are made of. When you hydrolyze them, you get those glucose, hundreds of them out of this hydrolysis, correct? So we have starch. Starch is made of 80% amylopectin and 20% amylose. All those are, when hydrolyzed, they give you what? They give you glucose. Now, let's go for looking at the test. So we have 3 tests. We have the Benedict's test. We have the Selenoff test, and we have the iodine test. So the Benedict can tell us if we have, will not tell us if we have a monosaccharides. That's easy to recognize. Or in general, any sugar will have the whole thing. So Benedict is a cover solution. I'll give you then. I'll post this one. What Benedict is. So the cover solution is being. So the first reaction here. The first reaction is cover 2 will be reduced. That's a reduction to cover 1. To cover what? Cover 1. That's a reduction. The sugar, or the whatever you have, the sugar here, the
will be going to carboxylic acid. Carboxylic acid. Here it is. This is the reaction here. That's a glucose. And you add to this Benedict solution, which is copper solution. And then what will happen here, this aldehyde will be oxidized to carboxylic acid, correct? And that's what the whole thing. And the copper here will be reduced to copper 1 oxide. To what? To copper 1 oxide. So this is reduction, and this is oxidation. And this is oxidation. So we have both reduction oxidation reactions. So the sugars being oxidized by Benedict solution, and Benedict solution, which is copper 2, will be reduced as copper 1. So this is a reduction oxidation reaction, and then we can verify those carbohydrates. However, the good test for this Benedict is to eliminate what? Sucralose. Sucralose is not going this oxidation reduction because it's missing this galopsidic connection. So if I take this one out, show you here, back up, you can see this is maltose, correct? The first one, this is maltose. This is maltose here. Now this is very important for oxidation. This is very important for oxidation. If this is missing, then there will be not oxidized. So the sucralose does not have this one here. So this is not, it does not have no glycosidic bond. Oops, sorry, bond. No glycosidic bond. So therefore you can see, because we don't have a bond there, so there will be sucralose gives you negative reaction for Benedicts. So therefore we have eliminated sucralose, which is made of glucose and fructose, eliminated out, correct? So that's the reaction of Benedicts will eliminate the sucralose, which is made of fructose and glucose. So there is no reaction. With the rest, there will be a reaction, correct? And the reaction, you can see it, it will give you the dark red, bright color. So you can see it here. It is, that's the Benedict's positive color. It is, so here it is. That's a reaction here. That's a positive for Benedict's reaction, correct? So next is to take the reaction and add Selivanov test for ketones and aldose. So the Selivanov test, you don't have to, I'll post for you what Selivanov reagent is made of. So when you put in the aldose, it will give you pink color. This is for aldose. And if you put it in the ketones, it will give you this color. This is pink, and this is red, dark red. So we use the Selivanov test or reagent to specify which is a ketose, which is the ketose means coming from ketone, or which is aldose coming from aldehyde, the sugars, correct? So this is the test. The last test is iodine test. Well, iodine test is positive for polysaccharides, cellulose, starch, glycogen.
So those we can use iodine for them. Iodine will make a complex. This complex will be looking like this. So this is iodine here itself. So this is iodine solution. No reaction. This one here is a complex. Dark blue solution. This is reaction. So we can determine if we have a polysaccharides with iodine will make a dark blue solution. So now how we hydrolyze those? We hydrolyze those by adding to them HCl, hydrochloric acid, as an acidic medium, and under water bath, boiling water bath. We don't overboil, but at least we make sure that's really warm enough. So if we boil, then we don't overboil. So what will happen here? Then you add HCl, and then you add HCl to this carbohydrate, to these sugars, and then you put them in the boiling beaker on the hot plate, and you can break them down. Like maltose will give you 2 glucose, like maltose will give you 2 glucose, and the starch will give you multiple of glucose. So they will be break down when you add HCl to them. Now in the body will break those carbohydrates by specific enzymes. But in our lab, we don't have enzymes, so we use hydrochloric acid instead. Okay. Okay, guys, so if you look at this test for hydrolysis, as I said, we'll do this one in the whole lab will be done inside the hood today, and you will do all the reaction inside the hood. You will not do it inside on the bench, correct, guys? And then the last test is hydrolysis. As I said, hydrolysis is you use after adding HCl. Okay, guys, after adding HCl, you get these test tubes, move them down, and then you will add to them Benedicts, correct, to test them for being what? To eliminate sucrose. Sucrose will not give you any reaction with Benedicts. And you do iodine testing to test them if they are polysaccharides, such as starch. Today we'll use starch, or cellulose, for example. Cellulose is polysaccharides. So I'll stop here. I think everything is explained itself. And if you have any question, just let me know. I'll be more than happy. And here's the hydrolysis. As I said, you can put HCl inside those sugars, boil them a little bit, not overboil them, cool them down, and then you add to them the HCl, and then you add to them by themselves. Those two different sub-experiments, not in the same time you add iodine and you add the Benedicts. No, first you take some portion of them to add Benedicts, and then some other portion to add the iodine. Thank you guys very much, and I'll stop here.